Imagine trying to tune a radio to a clear signal, but you have no idea what the broadcast is supposed to sound like. This is the fundamental paradox of unsupervised learning. How do you optimize a model's settings when you don't have the labels to tell you if you are right? The authors of this paper present a solution that uses the data itself to guide the tuning process. Subspace clustering algorithms are powerful tools for grouping data, but they often fail if their internal settings, or hyperparameters, are not tuned perfectly. Typically, finding these Goldilocks settings requires running a grid search and checking the results against known labels. But in real-world scenarios, like medical imaging, those labels simply do not exist, leaving researchers guessing in the dark. To solve this, the researchers propose a method that looks for internal stability, rather than external validation. The core idea is simple. If a clustering result is robust, a tiny change in the hyperparameters should not drastically change the outcome. By treating the model's own predictions as pseudo-labels, the system can measure how stable its answers are across different settings. Here is how the proposed method compares to the ideal oracle scenario. The oracle optimizes the algorithm by checking against the true answers, something you can basically never do in practice. In contrast, the self-guided approach iteratively compares the results of step I with step I+1. It searches for the parameter interval where the grouping remains most consistent, assuming that stability correlates with accuracy. Since the system operates without labels, the researchers introduced a visual sanity check to ensure the results make sense. They reconstruct images from the learned cluster subspaces. If the algorithm is working, you see clear digits or faces emerging from the data. If you see static noise, it means the search space needs to be adjusted. The results of this self-guided approach are surprisingly competitive. When tested across standard datasets, like MNIST digits and YLB faces, this blind tuning method performed within 5 to 7% of the oracle method that had access to all the answers. In some cases, like with the ORL dataset, the performance difference was statistically insignificant. This work is significant because it finally allows us to deploy powerful subspace clustering algorithms in the wild, where labels are scarce. By validating that internal stability is a strong proxy for accuracy, the authors have provided a way to process new, unseen data with confidence, without requiring a human loop for optimization. By turning the model's consistency into its own guide, this paper demonstrates that we can tune complex algorithms effectively even when we are flying blind. For more insights on this research, visit emergentmind.com.